Hello, today we're talking about automated parcel classification and tracking system.
For team members, we have Thammasorn, Theeramath, Watcharawit.
Contents, we have purpose, background and context, scope and objective. Methodology, we have calculation and categorization, challenge and solutions, results and conclusion. Purpose, the purpose of this project is to develop an automated computer vision solution for logistic environments. The system replaces manual counting by detecting, tracking, and categorizing parcels on a conveyor belt system using real-time video analysis. The objective of this project is to implement an automated computer vision solution for logistics environments. The system is designed to replace manual counting by employing real-time video analysis for the detection, tracking, and categorization for parcels for a conveyor belt system. Background and context. In modern warehousing, inventory throughput is high. Manual counting is prone to human error and fatigue. This project utilized OpenCV and Python to create a non-intrusive monitoring system that can operate 24 hours. It focuses on identifying cardboard-colored objects and maintaining their identity as they move through the camera's field of view. In the contemporary landscape of modern warehousing, a significant challenge is the inherently high throughput of inventory. Traditional manual counting methods are demonstrably susceptible to human error and efficiency degradation due to fatigue. To address this critical operational inefficiency, this project leveraged the robust capabilities of OpenCV and the Python programming language to engineer sophisticated, non-intrusive monitoring system designed for continuous 24 hours operation. The system is specifically optimized to perform real-time identification of cardboard color objects and, crucially, to maintain their persistent identify and tracking as they traverse the camera's field of view, thereby ensuring accurate inventory oversight. Scope and objective. Persistent tracking. Unique identifiers are assigned to each detected parcel, implementing a robust tracking mechanism to ensure accurate singular counting. Size classification. Parcels are mathematically categorized into three distinct size classes, which are small, medium, and big, based on calculated dimensions. Redundancy. A comprehensive triple-zone validation architecture is integrated to mitigate the risks of miscounts, specifically addressing potential ambiguities arising from varying lighting conditions or temporary object occlusion. Methodology. Image processing pipeline. The system employs a sequential pipeline to process and clean the raw video data. The first one is color space transformation, which is conversion from BGR to HSV color space is performed to isolate the targeted cardboard color range. The second one is image denoising. This involves applying Gaussian blur and subsequent morphological operations. Specifically, the open operation is utilized for removal of isolated noise, and the close operation is applied to fill small interior holes. The last one is frame segmentation. The frame is horizontally divided into three distinct zones to prevent the erroneous meshing of contours belonging to separate parcels.
Alright, so moving on to the next part of our methodologies. This is the tracking algorithm. So we use centroid tracking in this methodologies. So the system calculated the centroid coordinates x and y for every detected bounding box, and the tracker uses the Euclidean distance formula to mesh centroids between frame t and frame t plus 1. And here's the formula that we use to calculate. Next is the third part of our methodologies. So in this methodologies, we use triple zone validation. So to mitigate the issue of detections, a triple zone validation mechanism has been implemented in this project. So the first zone is on the left side, defined between 20 and 25% of our total screen width. The second zone is in the middle, which defined between 45 to 50% of the total screen width. And the last zone, the third zone, is on the right side, which is defined between 70 and 75% of our total screen width. And upon the centroid entering any of this defined zone, the system verifies its presence within the counted set. If the object ID is confirmed as null, then the total count is incremented. Alright, so here's the calculation and categorization. So the system classifies parcels based on the pixel area, which is area equal to width times height. And the categorization threshold are defined as small is smaller than 9,000, medium is between 9,000 to 18,000, and big is categorized by greater than 18,000. Alright, so let's begin with the main flow, which is the parcel tracking system flowchart. Well, this flowchart shows the main workflow of the parcel tracking system. Well, first, the system loads the input video files and initialize important variables such as the centroid trackers, the object counters, and the size classification variables. And next, the video is processed frame by frame. Each frame is resized to maintain the consistent measurement and then converted into the HSV color space. A Gaussian blur is applied to reduce noise in the image. And after pre-processing, the frame is divided into 3 conveyors. So first is top, middle, and bottom. And for each lane, the system applied HSV color threshold to detect cardboard parcels. So the morphological operation are then used to remove noise and fill small holes. The system then detects contours and filters them based on the area and width to remove unwanted objects. Valid contours are converted into bounding boxes. These bounding boxes are sent to the centroid tracker to track objects across frames. For each tracked object, the system calculates the parcel area and classifies it small, medium, or big. And finally, if the centroid of the parcel enters one of the counting zone, the system increases the total parcel count and updates the site statistics to the processed frame and system dashboard are then displayed until the video ends or the user pressed the Q key, which is exit. And next flowchart is the centroid tracker flowchart. So this flowchart describes how the centroid tracking algorithm works. And well, let's begin with the first step. The tracker receives the bounding boxes detected in the current frame as the input, and it first calculates the centroid of each bounding box. If there are no currently tracked objects, the tracker registers new object and assigns them unique IDs. If the objects are already being tracked, the system calculates the distance between the previous centroid and the new centroid using a distance matrix. And the tracker then matches the old object with the closest new centroid and update their positions. If an object is not detected in the current frame, the system increases its disappeared. When this counter exceeds the maximum allowed value, the object is removed from the tracking. And if new centroids appear that do not match any existing objects, then they are registered as new tracked object. And finally, the tracker returns the updated list of tracked objects and the centroids. And the last flowchart here is the system overview flowchart to show you the architecture of this project. So this diagram presents a high-level overview of the parcel monitoring system. So the process begins with video input from the conveyor belt system. Each frame of the video is processed to prepare it for analysis, and next, color segmentation is applied in the HSV color space to detect cardboard parcels, and after the segmentation, contour detection is used to identify the shapes of potential parcels, and from these contours, bounding boxes are generated to represent the detected objects, and the bounding box are then passed to the centroid tracker to maintain the object identities across the frames. And the system then measures the area of each parcel and classify the size as small, medium, and big. Next is zone detection, determines whether the parcel crosses the predefined counting zones. And finally, the system updates the parcel count and display the monitoring result on the output screen. All right, and here's the challenges and solution. All right, so here's the challenges and solution. So the first challenge that we have faced is the shattering problem. So one box was sometimes detected as several small pieces due to the shadow or the tape. So the solution that we applied on this is a large morph_close kernel, which is 25 times 25 to merge fragments into one object. The second challenge that we have faced is the ID blinking. So if a box disappeared from one frame, it could be treated as a new object. So in this case, the solution that we applied is to increase the max disappeared to 100 so that the tracker keeps the same ID even if the box is briefly lost. And the last problem that we have found is the double counting. So a box staying in the counting zone could be counted multiple times. So the solution that we applied on this is we used the Python set counted_IDs to store the unique IDs, so each box is counted only once. Next is the result and conclusion. So the final system achieved high accuracy using the triple zone approach. Even when detection was unstable, the 3-zone ensured the parcels were still detected during the transit, to reducing the missed detection and misclassification. And this multi-layer detection helped it maintain the reliability of the performance under the different lighting and environmental condition. And the size classification method based it on the Euclidean geometry and color filtering provided the consistent data for logistic planning. And overall, the system shows that the combining simple computer vision techniques with the computational geometry can create an effective and maintainable solution for the industrial automation. Thank you for listening to our presentation. This is all of our presentation. And next, let's move on to the demo part of our project.
Let's look at the code at the top from here until here. This line is where we initialize a central tracker and a max disappear value of 100. It is crucial. It allows the system to remember a box even though if the camera is lost sight of it for a few frames due to glare or any loss. We also set up our state variable, a Python set to hold unique count IDs and directional to track the area and size counts. Finally, we define our SSV color threshold to specifically target the color of the cardboard, which is much more reliable than using standard RGB. Okay, let's move on. In this while loop, inside the main loop, we first standardize the video width to 1000 pixels, so our math stay consistency right here. And then we convert the frame to HSV. And then we apply a Gaussian blur to remove sensor noise. Next is come to a very important structure step, land splitting over here. Okay, we mathematically divide the screen into 3 horizontal sections, top, mid, and bottom. By processing this lane independently, we prevent the system from accidentally merge two side-by-side blocks into one object. Here, inside our lane processing loop, we create a binary mask using a cardboard color threshold. To clean the mask, we use morphological operation. The mop open function removes tiny white speck of the background noise. The mop close function acts like a digital glue. It fills the dark holes inside the box caused by shadow or shipping label. Ensure the computer sees one solid shape. So, move next. Once we have our bounding box, we pass them to the centroid trackers right here. So after we finish the bounding box, we pass them to the centroid tracker, which assign a unique ID to each box to calculate the size. We find the closest bounding box to our trackers. Central using Euclidean distance, we calculate the area by multiplying the width and height and save it to our object areas memory dictionaries. This ensures that even if the box shape flickers, we always have the most recent size log right here. So next is the width area calculation. Classifying over here is the classifying area. So after we label it, we send it to the classifying algorithm. We classify by calculating the area of the box. If the parcel has the pixel area is 18,000 or greater, we label it as big. If it's between 9,000 and 18,000, we label it as mid, which is short for middle, and if anything smaller is small. Okay, next here, this part. So we finally reached the counting logic. Instead of a single type whip, I engineer a triple zone validation system. We define 3 vertical gates across the screen. If the box center dot enter the zone 1, zone 2 or zone 3, the system check if the box ID is already in our count ID set. If it is new, it gets added to the set and total count goes up. The act guarantees that mathematically impossible to count the same box twice, while the three zones provide a safety net in case the box is temporarily obscured. So, the final scene, the last one, is where everything show out. So, this is where the UI come in. So, after every algorithm that I create, the final result is rendered onto the heads-up display, showing the total count and the size breakdown in real time. So, for the lastly, I want to show you the result of the program I create. Here's the result. As you can see, there's 3 zones and the ID for each box, and it's count every time the box pass this 3 zone. Okay, thank you very much.